Hi everyone, welcome back. Today we're talking about hyperbolic functions. Now, these hyperbolic functions are embedded in the realm of hyperbolas. And we've extracted here these ideas that we can define a hyperbolic trigonometric function, in this case, hyperbolic sine of x, hyperbolic cosine of x, and hyperbolic tangent of x in terms of exponential functions. So on the screen here at the top, I have three different graphs. The first graph on the left, I have hyperbolic sine of x. Hyperbolic sine of x is made by taking the addition of 1/2 e to the x and negative 1/2 e to the negative x. If we take every corresponding point, or let's say every corresponding y value for every x value, add them together, we will get the resulting graph to be hyperbolic sine of x. Hyperbolic cosine of x is made by adding the two exponential functions. The first one is 1/2 e to the x. The second is 1/2 e to the negative x. When we add these two functions together, we get the hyperbolic cosine of x. And then finally, working with hyperbolic tangent of x, in order to get hyperbolic tangent of x, we must take the ratio from hyperbolic sine of x and hyperbolic cosine of x. Now, that ratio for hyperbolic tangent is very, very similar to the trigonometric ratio for tangent of x. So we must keep in mind that we do have a lot of similarities, and these hyperbolic functions are oftentimes referred to as hyperbolic trig functions. Within that respect, I want you to look at hyperbolic tangent of x. Hyperbolic tangent of x has two asymptotes, two horizontal asymptotes, one at -1 and the other at +1, which means hyperbolic tangent of x is bounded. Also, notice that all three functions, the two outer functions, hyperbolic sine and hyperbolic tangent, they are both one-to-one functions. However, hyperbolic cosine is the only one that is not a one-to-one function. And we could get it to be a one-to-one function if we were to restrict its domain. So we must keep that in mind when we want to take some derivatives, or let's say some derivatives of inverse functions, that we do get a one-to-one function, or that we do start off with a one-to-one function. Now, right below the leftmost graph, you will see these hyperbolic functions defined. We get that the hyperbolic sine of x, this is going to be denoted as sin h, and then parentheses, this is now the function of x. So again, hyperbolic sine of x is equal to the exponential function that is e to the x minus e to the negative x, all divided by 2. Hyperbolic cosine of x is defined by e to the x plus e to the negative x, all divided by 2. And then, as we discussed before, hyperbolic tangent of x is defined by hyperbolic sine of x divided by hyperbolic cosine of x. And then we define their cofunctions very, very similar to the trigonometric cofunctions. Hyperbolic cosecant is simply the reciprocal for hyperbolic sine of x. Same thing for hyperbolic secant of x, it is the reciprocal for hyperbolic cosine of x. And hyperbolic cotangent of x is the reciprocal for hyperbolic tangent of x. So we do get these hyperbolic functions that we work with. And again, these hyperbolic functions are embedded in these exponential functions that we now know how to work with to take their derivatives or their integrals. So we must keep that on the back of our minds. Now, on the right-hand side of your screen, you're going to see these hyperbolic identities. And these hyperbolic identities are the identities that are going to be satisfied whenever we start looking at these hyperbolic trig functions. And again, notice all of the similarities between hyperbolic trig functions and the regular trig functions that we're used to. Right? There's all these similarities, and within that respect, we could then start analyzing some of these, let's say, proofs or some of these techniques a little bit quicker by identifying these identities or these patterns. Within this respect, you will then see that hyperbolic tangent and hyperbolic sine of x, they are both odd functions. Typically for an odd function, you have symmetry along the origin, and that's exactly what we see graphically on the leftmost graph and the rightmost graph, that we have symmetry about the origin. Also, you can see working with algebraically, or working with the algebraic technique for hyperbolic identities, we get that hyperbolic sine of negative x is still equal to negative hyperbolic sine of x. And again, this now classifies it as an odd function. Very similarly, hyperbolic cosine is defined as an even function. Geometrically, because we can see it on the middle graph, it is reflective across the y-axis. Naturally, if it is reflective across the y-axis, well then we have an even function. So these are the identities that we want to, again, work with. So let's go on and let's prove one of these identities to see how we kind of work with this identity and how you might go about on proving some of these, let's say either on a home. Okay, so what we're going to do is we're going to identify one of these functions, and we now want to apply some sort of calculus to this. Well, one of the nice processes here is going to be if we consider the derivative, let's say with respect to x, for hyperbolic cosine of x. Well, remember, hyperbolic cosine, at the end of the day, hyperbolic cosine is represented by an exponential function, so you want to treat it as such. There we are. Now, going through the whole process, all we need to do is take the derivative for e to the x and the derivative for e to the negative x. That's it. The denominator is a constant, which means if we take the derivative of this rational function where the denominator is a constant, then the denominator stays as a constant. Now, taking the derivative of e to the x, we get e to the x back itself. Taking the derivative of e to the negative x, well, that we use the chain rule, and we get negative e to the negative x, all divided by 2. Now, look at this result, e to the x minus e to the negative x, all divided by 2. That should signify that this is your hyperbolic sine of x, which means that these derivatives for these hyperbolic trig functions are cyclic, very much like your regular trigonometric functions. So what we're going to do really quick is we're going to make sure we write these derivatives out. That way we know how to work with these derivatives. Alright, so here we are. We have these derivatives of hyperbolic functions. And again, we saw when we took the derivative of hyperbolic cosine of x that we ended with hyperbolic sine of x. Very similarly, when we take the derivative for hyperbolic sine of x, we will end with hyperbolic cosine of x. Similarly, derivative of hyperbolic tangent of x will lead us to hyperbolic secant squared of x. And we further have more derivatives for these hyperbolic functions, hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. We can all take those derivatives as well. So again, we have a nice summary here of these derivatives of hyperbolic trig functions. And moving forward in the course and for future math courses, you might want to refer back to these when you get a chance. So for now, you must commit them to memory because we will be using them as we move through the course. So here goes your first example. We want to find the derivative and we want to simplify where possible. The first function that we're going to be working with is going to be f of x is equal to e to the power of x multiplied by hyperbolic cosine of x. Now, looking at this function, what I see first that needs to be done here is going to be that we need a product rule. So when we work with the derivative, let's say f prime of x, I'm going to be using the product rule. Take the derivative of the first function, that's e to the x itself, multiplied by hyperbolic cosine of x, add it to the first function, multiplied by the derivative of the second function. The derivative of hyperbolic cosine of x, as we can see from above, or as we derived from above, will be hyperbolic sine of x. And there we are. Now, on a quick side note, the equation at the top of your screen, the one that we derived for the derivative for hyperbolic cosine of x, this was one of the hyperbolic functions, or let's say one of the exponential functions that was given to you on a discussion, and what you had to do was you had to take the limit definition of a derivative in order to find the derivative of that exponential function. Turns out that you can do this rather easily without using the limit definition, which make things a little bit more convoluted, however totally possible, but it still gets you the same answer. So for my first function, here we are. I am pretty much done here. If I wanted to, I could factor out a common factor, or in other words, a GCF, which is e to the x, and then we still have hyperbolic cosine of x plus hyperbolic sine of x. So there's our final result. Let's look at part B. Part B, we're going to have f of t is equal to the natural log of hyperbolic sine of t. Now again, going through the whole process, what we're going to do in order to take this derivative, we take the derivative of the outer function, and that's going to be 1 over the argument of hyperbolic sine of t multiplied by the derivative of the inside function, and that's hyperbolic cosine of t. This ratio here will then suffice to say this is really hyperbolic cosine of t divided by hyperbolic sine of t. That ratio leads us to hyperbolic cotangent of x, and we're done. That's it. So having these hyperbolic functions is definitely beneficial, and it's definitely helpful to establish that we can observe, or that we can take these derivatives without expanding and without representing hyperbolic trig functions in terms of their exponential functions. All right, we can keep them condensed and we can work with that function. Now, one of the other items that I want to look at is going to be hyperbolic cosine. Okay, so that's where we want to start. And in order to do this, let's see, here we go. I'm going to say let y equal to inverse hyperbolic cosine of x. And what we're going to do here is we're going to try to get an expression for its inverse, or in this case for its inverse hyperbolic cosine. All right, so here we go. So what we want to do now is we want to then work with this hyperbolic inverse function. Now, this hyperbolic inverse function, what we're going to do is we're going to say that x is going to be equal to hyperbolic cosine of y. And again, we're treating this as we're taking an inverse, that hyperbolic inverse and hyperbolic cosine are, hyperbolic cosine and inverse hyperbolic cosine are inverse functions of one another. In doing so, the left-hand side here, hyperbolic cosine of y, then becomes e to the power of y plus e to the power of negative y, all divided by 2. And all of this is equal to x. Well, again, what we're trying to do is we're trying to solve for y to make sure that we can get an expression for inverse hyperbolic cosine of x. In order to do this, we must be able to solve for y. So let's go through and let's attempt to solve for y. Alright, so I'm going to put here that we are trying to solve for y. Now, this is going to be easier said than done, so put on your algebra boots and we're going to get to walking. Here we go. We're going to multiply by 2. So this is going to be e to the power of y plus e to the power of negative y is equal to 2x. Good so far. I'm going to now say e to the y plus 1 over e to the y is equal to 2x. This is again because e to the negative y gets us a reciprocal. Then I'm going to multiply both sides of the equation by e to the y. This will give me e to the 2y plus 1 is equal to 2x times e to the y, to the power of y. Now again, we are trying to solve for y. So let's go ahead and get everything, all of the terms onto one side. This is e to the power of 2y minus 2x e to the power of y plus 1 is equal to 0. Now, we are trying to solve for y. It is okay if we have a variable x left over when we solve for y. Simply because at the very beginning, when we started, we defined y to be equal to inverse hyperbolic cosine of x, meaning x is the variable, or in this case, y is a function of the variable x. So when we solve for y in this equation here, it's okay to have a variable x left over because we will be counting on that variable. So let's see how we're going to go about this. This equation here, man, this is really neat right here. This is a quadratic equation. Check that out. That's a quadratic equation. If it's a quadratic equation, we can solve by using the quadratic formula. So we're going to use the quadratic formula naturally. And we're going to say that e to the power of y is going to be equal to negative b. So negative b is this whole term, which is negative 2x. So negative 2x plus or minus square root of b squared. So that's going to be negative 2x squared minus 4 times a, which is 1, times c, which is another 1. All divided by 2a. Oops, excuse me. There we go. Perfect. So now let's go ahead and simplify this a little bit more. E to the power of y is equal to 2x plus or minus 4x squared minus 4, take the square root of that, all divided by 2. Notice the radicand can factor a 4, so we're going to go ahead and factor out that 4, and when that happens, the whole numerator has a factor of 2, and the denominator has a factor of 2, which then naturally means that we get x plus or minus square root of x squared minus 1. Now, how do we solve this? Well, the way we solve this, or the way we solve for y is by taking the natural log of both sides. And in doing so, we wind up with this formula. As such. Now, this formula will now give us insight into what y is. Because look, we now have two equations that are equal to y. By transitivity property, they must be equal to one another. Thus, we're able to get that inverse hyperbolic cosine is then equal to the natural log of x with a little domain restriction will be x plus square root of x squared minus 1. So, moral of the story. Inverse hyperbolic functions have representations, and these representations must be extracted in terms of natural log functions. So let's go ahead and let's write these down, making sure that we grab all of these inverse hyperbolic functions. All right, now here we are. So on the left we have your inverse hyperbolic functions, and on the right we have the derivatives of inverse hyperbolic functions. Now, when you attend class this week, we will be talking about, or let's say we will be working on deriving the derivative of hyperbolic cosine inverse, or the derivative of hyperbolic sine inverse, or the derivative of inverse hyperbolic tangent of x. So we will be working with some of those in class, and once again, it would be beneficial if you attend class. That way, if something like that happens to be on an exam, then you are prepared for that. Also, the derivatives of these the derivatives of inverse hyperbolic functions, you're going to notice that the two last derivatives on each column are the derivatives for inverse hyperbolic tangent and inverse hyperbolic cotangent of x, and they look very, very similar. And you would be right, the functions are similar, however, the values are going to be differently defined on a specific domain. For example, inverse hyperbolic tangent of x is defined for the absolute value of x is less than 1, where the inverse hyperbolic cotangent of x is going to be defined for the absolute value of x being greater than 1. So again, we have different domains in which we observe them in. Now, let's go through and let's start applying some of these examples. So, the first examples, they're going to be to find the derivative. And we're going to simplify where possible. So part A is going to be y is equal to inverse hyperbolic sine of tangent of x. Now, when you're taking a quiz or an exam, please pay close attention to the function. Do we have a hyperbolic function, or do we have a regular trigonometric function? That is what you have to pay attention to in order to be pretty successful for these calculations. So let's go ahead and let's start. We want to take this derivative. So again, we're going to be looking at dy dx for the function of inverse hyperbolic sine of tangent of x. Now, in order to take this derivative, what we're going to need to do is we're going to pull the chain rule. So the first derivative is going to be the derivative of the outer function, which means the derivative of inverse hyperbolic sine of x. So that derivative will then be 1 divided by square root of 1 plus the argument of inverse hyperbolic sine, which in this case is tangent of x, squared. I can do a better job writing that. Tangent squared of x. There we are. So that's a derivative for inverse hyperbolic sine of x, all right, or tangent of x. Now we need to multiply this by the chain rule, which says that we need to multiply by the derivative of the inside function. The derivative of the inside function is, or in this case, derivative of tangent with respect to x. The derivative of tangent with respect to x will be secant squared x. All of this is going to be divided by the square root of 1 plus tan squared x. Alright, so this is looking nice so far. Now, on the denominator here, I kind of see something that is really beneficial for us, and that beneficial aspect here is that 1 plus tan squared of x is a Pythagorean identity. That Pythagorean identity for the denominator, oops, excuse me, it's not C2, secant squared of x divided by, oh, that's a wavy line, divided by, I don't like that line, there we go, wavy again, there we go, that's good enough, divided by the square root of secant squared of x. Now you might say, hey, that looks really nice. We can possibly cancel some stuff out there. You would be almost correct. Now remember the denominator. The denominator, we have to take the square root of secant squared of x. Now some of you might say, oh yeah, that's just square root of x. And I would caution you because it is not just this. It is not just secant of x. It will be the absolute value of secant of x. And the reason for this is that when we look at, let's say, when we look at the square root of x squared, this does not evaluate to just be x. This evaluates to be the absolute value of x, simply because any x value that you choose, whether it's positive or negative, will always evaluate to be the answer to just be x itself, whether we have positive or negative. If we insert negative 3 squared, square root of 9 is going to be 3. In other words, our original value was 3. And we can keep doing this process over and over and over. Okay, so now that we have that, secant squared of x. Notice, secant squared, well, another thing about secant squared is that if we work with, let's say, secant of x squared, well then this is still secant squared of x. Okay, it's just a notation that we use. So using that concept, you're going to notice on the left hand side for that equation that the quantity of secant is going to be squared. In other words, this is always going to be positive. What does that mean for us? Well, what that means for us is that we will have the absolute value of secant squared of x on that numerator. And this is a quality because, again, the absolute value has no effect on this secant squared because secant squared is already positive. It's a little redundant, however, it is beneficial because now we can simplify one of the secants of x in the absolute value, which means the overall result here, let me put this down here, the overall result will be the absolute value of the secant of x. And that's all there is to it. It's pretty good and straightforward. Let's try part B. For part B, we're going to have y is equal to inverse hyperbolic secant of e to the power of negative x. There we are. So when we work with this derivative, again, the first thing that we are going to look at is taking the derivative of the outer function. So again, we want to work with dy, d variable, what we have in this case, dx. And we're going to apply that derivative onto inverse hyperbolic secant of e to the power of negative x. Okay, so y prime in this case will be the derivative of inverse hyperbolic secant, which is negative 1 divided by the argument of inverse hyperbolic secant, which is e to the negative x. So this is e to the negative x multiplied by the square root of 1 minus its argument squared, which will be e to the power of negative x squared. This will then be multiplied by the derivative of the inside function, which will be negative x, e to the negative x. So, making this, let's say, derivative, taking this derivative will be negative e to the negative x. So negative times a negative will be a positive, and we're going to be left with e to the negative x, all divided by e to the negative x multiplied by the square root of 1 minus e to the negative 2x. E to the negative x's will simplify, and we will now be left with 1 over the square root of 1 minus e to the negative 2x. Let's write that better. E to the negative 2x. A little bit better. There we are. Okay. Perfect. Perfect, perfect. So as we can see, we start working with these hyperbolic functions, and we start analyzing and extracting what they could be and what they are. So let's try one more example. And this last example, I will say evaluate the integral of hyperbolic sine of 1 plus 4x dx. So again, now we're working with antiderivatives. In order to do this specific integral, I more than likely want to make a u substitution. So let me start off by saying I have the integral of hyperbolic sine of 1 plus 4x. This is going to be dx, where u is going to be the argument, which is 1 plus 4x, which means du is equal to 4 dx. Therefore, dx is just going to be 1/4 du is equal to dx. And making this substitution now, I have hyperbolic sine of my substitution, which in this case was u, dx. Well, that dx now turns into 1/4 du as such. In doing so, I have a constant, so I now factor out that 1/4, and this is now 1/4 times the integral of hyperbolic sine of u with respect to du. Now, the antiderivative for hyperbolic sine of u, well, that's just cosine, or hyperbolic cosine of u. This is an indefinite integral, which means we're left with plus c. And at the end of the day, we were not solving, or we were not evaluating the integral with respect to u, so I have to go ahead and make my resubstitution, or my back substitution, for hyperbolic cosine of, in this particular case, 1 plus 4x, and then plus my constant, because again, this is an indefinite integral. Now, if you stick around for class, we are going to work more on these examples for taking the derivatives and for evaluating these specific integrals. So I hope you all enjoyed this lesson, and I will see you all in class, or I will see you all next time.